hear you pull in. Thanks for stopping by. It's time for us to look at some more intersections. We looked at the intersection of two lines in 3 space. Now we're going to look at the intersection between a line and a plane, which obviously must be in 3 space if you're talking about a plane. And we're also going to look at the intersection of 2 planes. I love this time of the year. It's beautiful out. It's a great time to do some algebra and geometry. So let's get to it.
So let's start by looking at the intersection of a line and a plane, and let's consider the geometric possibilities about what might happen. The first possibility is that the line intersects the plane at one point. In this picture, that point is point P. Notice the line is called line L, and the plane they have called pi, which is actually a common name to give a plane. Another possibility is that the line, and the second possibility, the line is parallel to the plane. Now notice that red line is your line. It could be above or below the plane, but not intersect it because it's parallel. Now it's different to talk about a plane and a line being parallel than it is 2 lines. But in this picture we have a plane with a normal n, and that gives us the direction of the plane. For whatever reason, in this example, the direction vector of the line is called m. Now, if the line is perpendicular to the normal, that means it's going to be parallel to the plane, and that's exactly what we have here. We have a line that's perpendicular to the plane's normal. So that means if we were to dot the direction vector and the normal, we would get 0 here. And there is obviously no intersection or no solution. I know that's a bit backwards to think about. A line is parallel to a plane if it's dotted with the normal, it gives you 0, or if it's perpendicular to the normal, you get 0. And that's because normals are perpendicular to planes. And then the third possibility, and the last one here, we have a line that's in the plane. And so there's an infinite number of solutions, or infinite number of points of intersection. And the line itself is, in fact, the point of intersection, or the intersection. So in this case, m dot, if m was the direction vector of that line, m dotted with n would still be equal to 0. The line's still parallel to the plane. It's just in the plane. Okay, let's look at our first example. We've got a line given by the symmetric equation and a plane, of course, given by the scalar equation. So I might start by looking at the direction vector for the line and realizing that this line is not parallel to the plane. If I look at the normal to the plane, 4, -2, 1, remember I get that from the coefficients on x, y, and z. If I were to dot these two together, I would get, let's see, 2 times 4 is 8, 8 minus 6 is 2, plus 2 more is 4. So not 0. So we will get a point of intersection. I can determine that right away. Now, how do you actually find that point of intersection? Well, the easiest way to do it is to take your line and write the symmetric equation. In this case, it's x equals 1 plus 2t, y equals -6 plus 3t, and z equals -5 plus 2t. How am I getting that? Well, I have the direction vector, which I get from the denominator. And then I have the initial point, which is the opposite of these 3 points right there. That's how I'm getting those symmetric equations. Well, I then take my parametric equations and I sub them into the plane. So I'm going to take my x, y, and z value and sub them in right there, and I get 4 times 1 plus 2t minus 2 times -6 plus 3t minus 5 plus 2t minus 19 equals 0. We then expand and solve that equation for t. 4 plus 8t plus 12 minus 6t minus 5 plus 2t minus 19 equals 0. So how many t's do I have? Let's see, 8 subtract 6 is 2, plus 2 more is 4t. And for my numbers, I've got 16 minus 5 is 11. just check that. 16 minus 5 is 11, so minus 8 equals 0. So that's going to give me t equals 2. So what I found is that the parameter for the point of intersection happens at t equals 2. So I take that, I sub it back into the parametric equations to find the actual points of intersection. So x equals 1 plus 2 times 2. I get x equals 5 there. Y will be negative 6 plus 3 times 2, which is 0. I'm just getting that from this equation right here, right? I'm using these parametric equations right now. And my last one, z equals negative 5 plus 2 times 2. Z is equal to negative 1. And so I have a point of intersection here, and that's my solution right there, 5, 0, negative 1. Now, let's think about this for a second. We started with the geometry, imagining what a line looks like when it intersects the plane. But what about the algebra? Notice the algebra really just starts right here. We have to take one equation with one unknown and solve it. So my values of my t is my unknown, and this is my one equation. So really, finding the intersection of a line and a plane is exactly the same in some ways as finding one equation, one unknown. So the algebra side of this is one equation, one unknown. And when you solve an equation with one unknown, then that's exactly what you can expect if it's a linear equation. You can either get one solution, you can get no solution, or you can get an infinite number of solutions. For example, most equations have one solution, but you could imagine 3x equals 3x plus 1. That would have no solution. Okay, you get 0x equals 1. Or you could imagine 3x plus 1 equals 3x plus 1. There's an equation that has an infinite number of solutions. So let's just thought I'd bring that up. Okay, let's look at the next example. So in example 2, we have another line and another plane. Now, the first thing I've done right away, I took that vector equation and I changed it so it's a parametric equation. I'm then going to sub that into the equation of my plane, and I get 2t plus 4 times 1 minus t plus 2 times negative 4 plus t minus 4 equals 0. Notice I'm immediately, in this case, I decided to jump right into the algebra. I didn't consider the geometry part right away, and that's fine. Okay, if I solve this, I'm going to get 2t plus 4, take away 4t, minus 8 plus 2t minus 4 equals 0. Okay, putting my t's together, I get negative 2t. The t's have all actually canceled out. So for now, let's just say 0t. My numbers are 4, take away 8, which is negative 4, subtract 4 more is minus 8. So here I'm getting something like negative 8 equals 0, which is impossible. That can't happen. So there is no solution to this equation. I mean, when you solve an equation, the first thing you're doing is you're assuming that it's true. You're saying, okay, I'm going to assume this is true, and I'm going to find out what t has to be. When you assume something's true, and then you arrive at something that's clearly false, that means your original assumption was false, which means that this statement is false, which means it has no solution. Well, if there is no solution, that means that there is no point of intersection. So if our goal is to find the point of intersection, it's not going to happen. And sure enough, if we look at the line has a direction vector equal to 2, negative 1, 1. The plane has a normal that's 1, 4, 2. If I had, instead of jumping into the algebra, if instead I'd thought about the geometry, I would have realized when you dot these, you do in fact get 0. 2 minus 4 is negative 2 plus 2 gives you 0, which means that the direction vector and the normal are perpendicular. It means that the plane and the line are actually parallel, and we have this middle case up here. How do I know they're parallel and not the same plane? Well, the answer is actually in the algebra here. If the point of intersection had been infinite, I wouldn't have got this -8 equals 0. I would have got something else. We could have began the question by looking at this right here, but we don't have to. Let's try the next one. So it's another intersection of a line and a plane, but notice I've kind of thrown some different notation at you. Here's the equation of the line. It's really just a parametric equation, but instead of writing x equals, y equals, z equals, we wrote it in coordinate form. So this is like a point, x, y, z, and instead of giving coordinates of a point, I gave them in terms of a parameter. So that's not a super common notation, but you will see that from time to time. So we sub those values of x, y, and z into the equation of the plane to find the point of intersection. And I get 3 plus 14s minus 2 take away 5s plus 3 times 1 minus 3s minus 4 equals 0. Let's see what we get in this case. So 14 take away 5, subtract 9. The s's again are going to subtract out or cancel out. And in this case, the numbers 3 minus 2 is 1, plus 3 is 4, 4 minus 4, we get 0 for the numbers as well. So we get this equation right here when we simplify, which could be reduced to 0 equals 0. In this case, we assumed the equation was true and tried to find the value of s, and we arrived at something that's always true, which means that s can be any single number. And this is maybe a little easier to understand. You could plug in any value of s you want, and this equation would always be balanced because the s's just subtract out, and so do the numbers. So you probably realize by now that this is case number 3, where we have a line that is inside the plane here. And so our point of intersection is the line itself. So how do you write that? I don't know. You could say the intersection is a line, is the line. And then you could give its equation if you want to. That's one way to do it. Now, geometrically, we could have looked at this as well. We have a direction vector for the line that's equal to, let's see, 14, -5, -3. And for our plane, our normal was equal to 1, 1, 3. So we expect that the line and the plane are parallel. If the line is in the plane, they have to be parallel. Well, what do we get when we dot them? Do we in fact get 0? We get 14, take away 5, which is 9, subtract 9. So yeah, we do get 0 in this case. This doesn't tell us that the line is in the plane, it just tells us they're parallel. So how could we determine whether or not the line is in the plane or just parallel to the plane? Well, I mean, one way to do it is the algebra here tells us that the line is in the plane. We got 0 equals 0 as opposed to like 0 equals 3 or something like that. Another thing we could do, we do have a point on this line. That point would be 3, -2, 1. If we subbed that into the equation of the plane, we'd find that that point is on the plane. And if that point is on the plane and the plane is parallel to the line, then the whole line must be in the plane. So I'm just kind of comparing. Hopefully you see what I'm doing a lot of the time. I'm comparing the algebra to the geometry. So the next thing we'll look at is the intersection of two planes. So here you can see that there are also 3 cases for the intersection of 2 planes. And there they are. Case number 1, the 2 planes, pi1 and pi2, they might intersect along a line, in which case your intersection is a line. It's an infinite number of points of intersection, but they do form a line. Case number 2, 2 parallel planes. So in this case, there is, of course, no intersection at all. And then we should really consider the strange case where we might have 2 coincident planes, or 2 planes are the exact same. It seems kind of strange, but technically it's a possibility. In this case, there is a intersection. The intersection is the plane itself. So we either have a line as our intersection, no intersection, or a plane. Unlike the other 2 intersection scenarios we've looked at. We looked at the intersection of two lines in 3 space, and we've looked at the intersection of a line in a plane. The intersection of two planes, there is no possibility that you could have a single point of intersection or a single solution. We often talk about that being a unique solution. There's no x equals y equals z equals possibility in this case. Let's look at our first example. So all I've done to get started with this example is I've written the equations of the planes and labeled them equation 1 and equation 2. Now notice I've got them lined up nicely. And that's because I'm going to use elimination. Remember that elimination is the idea that you can add or subtract two equations to eliminate a variable. Keeping in mind that you could multiply one of the equations or both of the equations by a constant if that's what's required. In this case, I can see that if I take equation 1 and subtract equation 2, the x's will eliminate. I'll get negative 2 minus y, which is negative 3y. 5 subtract negative 4 is positive 9z, plus 3 equals 0. Now that's the equation 1 minus 2. And I have just y's and z's. What can I do with that? Well, one thing I can do is I can actually solve for y if I want. So that gives me negative 3y equals negative 9z, take away 3, and then divide everything by negative 3, gives me y equals 3z plus 1. Now, I understand using elimination in this scenario is much different than what you're used to. So we're not actually able to solve for x, y, and z. That's impossible, and we know that from the geometry part of it. But what I can do is now that I've solved for y in terms of z, I could sub that into either equation 1 or equation 2. Now notice equation 2 is quite a bit easier to work with in this case. So I'm going to sub that into equation 2, and you'll see why. I get 2x plus 3z plus 1 minus 4z plus 7 equals 0. Now I chose to use equation 2 and not equation 1 because if I'd used equation 1, I'd had negative 2 times 3z plus 1, which would have made it like, just a tiny bit harder, not really much harder at all. I can do the same thing. Notice here I have y solved for y in terms of z. I can do the same thing for x. I get 2x minus z plus 8 equals 0, or 2x equals z take away 8, x is equal to 1/2 z minus 4. Okay, what have I done? Well, I've basically done the best I can do right now. I can't solve this for x, y, and z. It's impossible. There's no algebra that works. Anything else I do right now, I'm just going to end up going around in circles. I start subbing this into one of the other equations, and I'm not going to get anywhere. And knowing the geometry, knowing that there isn't a unique solution to this, does help me realize that fact. But one thing I have done is I've expressed both x and y in terms of z. So really, z can be anything. X can be 1/2 of z minus 4, and y is 3z plus 1. That actually describes all of the solutions to this system, or to this intersection. So that's actually kind of like a line. So our solution could be, let z equal t, y is equal to 3t plus 1, because y is equal to 3z plus 1, and x is equal to 1/2 t take away 4. And that is actually the parametric equations of a line, and is my solution, because my solution in this case is in fact a line. Now that's one possible solution, but there is a better solution. It has to do with the 1/2 t. That's not necessary, because what I could do is I could say let z equal 2t, y is then equal to 6t plus 1, and x is equal to t take away 4. So I don't need the fractions if I just double my parameter here. It's kind of like in this example, you would say the direction vector was 1/2, 3, 1. Well, why not use 2, 6, 1 and not have any fractions? So that's actually our solution, and it is in fact the equation of a line. Now notice if I go back to the geometry, you realize that this helps us understand some of the algebra. In that algebra, what do I have? Well, I have two equations with three unknowns. So this is the algebra part. Two equations, three unknowns. And the geometry helps us realize that what is the possibility for solutions when you have two equations, three unknowns? Well, one possibility is no solution or an infinite number of solutions. It's not possible to solve three unknowns with two equations. It's kind of like you don't have enough information to come up with a unique solution. There aren't enough restrictions on the variables to come at a unique solution. Moving on to our next example. So again, I've rewritten those two equations, lined them up, labeled them as equation 1 and 2, and I'm going to use elimination. Now, if you want, you could double equation 1 and eliminate the x's, but notice that the z's are opposites of each other, so why not eliminate those? I add the equations together, I get 3x minus 2y, the z's are eliminated, plus 1 equals 0. Now, right away, you might have noticed that this is going to be different than the last example, because in the last example, we took x and we solved for x in terms, or we took y first, actually, and solved for it in terms of z, okay? Then we did the same thing for x. So we had x and y solved in terms of z. But when we eliminate z at the beginning, we can't do that. Well, one workaround would be not to eliminate z, but we can do it this way. It's fine. What I need to do now is I need to either solve for x or y. I'm going to solve for x. If I do that, I get 3x equals 2y take away 1, and x is equal to 2/3 y minus 1/3. So I've solved for x in terms of y. I now need to do the same thing again. I'm going to take this here, and I'm going to sub it into equation 1. When I do that, I get 2/3 y minus 1/3 plus y plus z minus 1 equals 0. Now, if you don't like the fractions in that equation, just multiply everything by 3, and you get 2y take away 1 plus 3y plus 3z minus 3 equals 0. Now, what do I do next? Do I solve for y or do I solve for z? Well, notice that in this equation, we have x is 2/3 y minus 1/3. It'd be really nice if we could then solve this equation the same way, which means we're going to solve for z, so we can also express z in terms of y. If you do that, you will get z equals negative 5/3 y plus 4/3. So now instead of solving for z, instead of solving for x and y in terms of z, I've solved for x and z in terms of y. Notice again, this is a line. Our intersection here is going to be a line. And one way to write the equation to that line is to say if y can be anything, then y equals t, the parameter. X is 2/3 instead of y, 2/3 t minus 1/3. And z is equal to negative 5/3 y plus 4/3. And then, of course, y is t. Y can be anything. It's our parameter. Now, a better solution, of course, is the idea that the parameter doesn't have to be y equals t. We could eliminate some of the fractions by making it y equals 3t. And if y equals 3t, then x equals 2t, take away 1/3, and z equals negative 5t plus 4/3. And this is a better solution right here. Now, although I was able to eliminate the fractions on the coefficients of our parameter, I can't do anything about the negative 1/3 and 4/3. Those, I can't change those. Those are actual points. So there's a solution. Now, one thing that might be a little frustrating for you is that if you wanted to, you could have started this problem by eliminating the x's, in which case you'd have an entirely different equation of a line. In fact, if you wanted to, you could eliminate the y's to start, in which case you'd have an entirely different equation. In fact, there's really 3 different equations of lines you could come up with. one where y is your parameter, one where z is your parameter, and one where x is your parameter. And since vector and parametric equations of lines are not unique, they would actually all represent the same line. Okay, let's look at our next example. I've labeled those equations as 1 and 2. Notice they didn't say anything in the question about finding the intersection. They just said solve the system of equations below. Well, we know that two equations with three unknowns, there's not going to be a unique solution. And we know that because those equations could be represented by planes, and planes can't intersect to give you a single solution, which would be represented by a point. If you want, we can continue thinking about this geometrically. Look at the normals for the first plane, or the normal, 1, 4, negative 3. And the second normal is 2, 8, negative 6. Well, n1 doubled gives you n2. So those are collinear or parallel normals, which means the planes are parallel as well. So either we have the same plane or we have two parallel but distinct planes. I wonder if you can tell which it is. Are they the same plane or are they different planes? I think if you look at these numbers here, you see the clue. If they were the same plane, it means they're the same equation. And if they're the same equation, then every value would be doubled, and we would see a 12 there, a positive 12, instead of a negative 9. So they are, in fact, different planes. So I can tell geometrically that there is, in fact, going to be no solution here. Now, algebraically, I should be able to show that as well. I could try to solve using elimination. I could take 2 times equation 1, and I could subtract equation 2, as if I'm trying to eliminate the x's. And I would eliminate the x's. In fact, it would eliminate the y's as well. In fact, it would eliminate the z's. But it would not eliminate the numbers here. You would have 12 take away 9, which is the equation, negative 3 equals 0, which is obviously baloney. So we know there's no solution. A similar example, let's just write these two out. 3x, take away 5y, minus z plus 2 equals 0. And 9x, take away 15y, minus 3z plus 6 equals 0. Again, if you look at it geometrically, you might realize the normals, the first normal is 3, negative 5, negative 1, and the second normal is 9, negative 15, negative 3. So one normal is 3 times the other, so they are collinear. And in this example, the constants, the 2 and the 6, are 3 times bigger as well. So really, this is kind of an unsimplified equation. You could divide everything by 3 and you'd have the exact same equation. So in this case, these are coincident planes. They're the same plane. So the intersection is just the plane itself. So the planes are coincident. Now, algebraically, how could we show that? Well, you could go 3 times equation 1, subtract equation 2, as if you're trying to eliminate x's. When you tried to eliminate x's, you would find that you not only eliminate the x's, you also eliminate the y's, the z's, and the constants, and you get 0 equals 0. In which case, there's nothing you can do with this system as you try to solve it. So the only thing you're left with is the simplified equation itself as the actual solution, the plane. Okay, thanks for tuning in, and I wish you the best of luck this week, and see you next time.